Great. So that now that we understand where the strain tensor comes from, we can now and we understand that normal strains and our shear strains change angles. I just want to quickly show you intuitively that when things are changing angles and not, is really a function of how we look at the world. So I can draw sort of a square here, and I'm going to try and draw it large. That is essentially now undergoing some kind of deformation. So let me get a different Koki. So it's not playing along. Yellow. Blue neither. Let's see if this is better. Alright. Hopefully orange is going to be better. Let's see. Okay, pink. Okay, so that is essentially what I have here. Okay, so if I go and I say this is what this deformed towards this place here. Okay, so we can think of it, I've got a structure here originally, and I've got a structure then essentially here that is sort of deformed now. And what I want us to think about is, okay, when I just look at it, when I draw the structure like this little square, I can see that there's been a change in angle. For instance, I can see that there's a change in angle there. We know that this is essentially 90 degrees minus the gamma. Let's call it gamma xy. This is now the xy plane. So that is essentially what we can see from this one. From this, okay. The whole question is if I'd maybe started off with not drawing a little square like this, especially if you think about that this is now sort of a differential, a dx and a dy. It's something I've drawn in the body. Okay. What would have happened had I, for instance, drawn the square maybe at an angle for it? What would have happened to that? And to try and answer that question, if I started with that, would that also have changed angles if it was a small differential element that was more rotated? We can look at that, ask that question by sort of drawing a little axis on here to start off with. So this is the axis that I start off with. And if I draw this axis here like that, and I look at the deformed state, I can see that the axis essentially, it was there and now it's sort of there. And those are the angles that I have. And we can see that that is happening. Okay, I could have also said, well, let's maybe draw a different axis on here and just look at what happens to the axis, then we don't have to worry about rotating the whole square. So if I had drawn an axis maybe that was oriented like this, okay, and I'm going to just draw this line right through here, that is clear. If I'd started off with that, how would that thing look in a deformed state? So let's start off with this. If I said, this is my axis that I'm looking at, how would that look in the deformed state? Essentially, what the reality is, this would have been, this point would have now moved along towards somewhere here, so that would have been there, but it would have remained on this kind of line. And if I ask myself what would have happened with this, is that would have just sort of contracted or stretched, really. It would not have changed directions. So let's just make sure I draw it sort of there, and that sort of angle, this one, going through that direction there, essentially would have just contracted. But what I'm seeing here is I started off with a 90-degree angle and I'm still sitting with a 90-degree angle. I'm not seeing a change in angle now. What is going on? Well, what's going on is just we are looking in a different reference frame to exactly the same state. This is still the same body that's deformed to exactly that same shape. The only thing I'm doing is I'm not looking at a coordinate system that is like this now. I'm asking myself, what happens if I were to say this is the coordinate system that we want to look at things? Then I'm seeing a very different behavior. And the importance of this is that when we think about normal, like tensile stress and strain, or tensile strains, or compressive strains, or shear strains, it's really a function of the coordinate system in which we want to try and express. And what is important is that we understand that there's a way of looking at it that will maximize sort of the tensile stresses that we'll see, or tensile strains that we'll see, and there's a way of looking at it that will sort of maximize what is the sort of shear strains that we might see. And the reason why that is important is materials fail for different reasons. So if you have sort of a brittle material, typically pulling and pushing on that, especially pulling tensile loads on a brittle, it's not a good idea. And it typically fails, brittle materials typically fails due to tensile kind of stresses. So tensile strains is sort of a bad idea for brittle materials. But if it comes to something like the more ductile material that you want to form plastically or something like that, then it's really shear that dominates that and drives that kind of behavior. So that's, again, you want to see what is sort of the maximum shear kind of conditions at a point in the material. So what is important to take home from this is just by changing just the way we express what we're looking at, we can look at the world and say, oh, things have changed angles, or we can say, oh, nothing has changed angles, things have just sort of stretched in those directions. Okay, so that is important to understand. Hopefully this will give you just an intuitive understanding in terms of what's going on. So what is important for me is that when you look at something and you look at the deformations and a certain coordinate system, observe and see if angles are changing. That's the easiest way to spot that shear is present. So that's always the key that you need to look at. And the rest is just pulling and pushing kind of compressive and tensile kind of loadings. Okay, great.